Okay, so what we're looking at, again, we're looking at longitudinal shear, right? And we looked at an analysis of a beam where this is fairly similar to the first analysis we did. A simply supported beam, right? We've got some loads, concentrated loads, distributed loads. This is the cross section, right? Last time we looked at the shear at the bottom face of this top section, right? And the question comes up, well, what happens if what about vertical components? Well, let's see, horizontal components on the, let's say TXZ, right? So remember, when we talk about tau XY and tau XZ, we're talking about the, let's see, the X facing, or the plane that's perpendicular to the X direction, right? So we'll be looking down at this plane, and the Y direction, that's vertical, right? Now we're going to look at tau XZ. So we've got the X plane that's pointed perpendicularly, well, pointed out the X, oh God, the X plane, which we're looking down on as we look down the X axis, right? And we're looking at the Z component of stress. So what's the stress coming off in the Z direction? And one interesting way to do that is to look at this is, now this cross section here looks the same as the one we analyzed last time. It just looks like a slice. But if you look at it from here, it looks like, it looks like someone took a bite out of it. It's got a curved, it's an arc, right? It's got a curved surface area. So we can do the analysis the same way as before. We can do sum of the forces equals, in the X direction equals 0, right? And we've got the normal force on D, the normal force on C, right? Face C and face D were the, based on the locations. We've got this delta H, right? The force per unit length. Sorry, the delta H is the force, Q is the force per unit length. We want to figure out what H is, right? We do the same basic formula, right? It's H plus the difference between these two, sigma D and sigma C. And we find out basically that we get the same equation as before, right? So the point is, it doesn't matter if you're looking at, the bottom section of this cut or the side section of this cut or some kind of angle in between, right? You still have the same formula for that. And we're going to use that idea with this box beam. So notice the way this box beam is constructed, right? Instead of being rotated 90 degrees and having a continuous flat surface with seams, on either side like this, it's tilted on its side, and the seams are, you see the seams here, they're vertical, right? And it's constructed with nails. So here we are with the nails again. The spacing between nails is 1.75 inches. Again, that's the spacing. If you're looking at the beam in and out of the page, right? That's the spacing. You have one nail, and then you come 1.75 inches closer, and you got another nail, 1.75 inches closer, another nail, or again, going the opposite direction. Oh, the beam itself, right, has a vertical shear. It's subjected to a vertical shear of 600 pounds. Determine the shearing force in each nail. So what we're going to do here is we're going to do the same thing we did for one of the earlier problems, except now we're looking at it on the side. We're going to do the shear force per unit length along the edges, right? Those vertical edges here. These vertical edges. And then based on the spacing and the number of edges, we can figure out the force on each nail. This one I'm just going to walk through. I don't have it on paper. Oh, you know what? I didn't put the other one on paper. All right. So let's look, probably should have done this in a different manner, but let's look at the system, right? The general equation, which is down, oh, here it is, Q equals VQ over I, right? We require the shear, that's 600 pounds. we require Q. Well, what's Q? We're looking at the upper plank and we're looking at this seam here, vertical seam. And if you look at the entire upper plank, we've got an area that's the thickness, right? 0.75 inches. We're looking at this shaded region here, 0.75 inches by 3 inches, right? That's your area. That's this thing. And then the Y, the distance from the centroid to the neutral axis, is this 1.875, right? This is just geometry or algebra, it's just math. That gives you Q. So remember, that's Q for that part. And this part is in contact on two sides, right, with the rest of the components. And then the overall beam cross section is basically this, it's two squares, right? You've got the outer square, so 1/12, 4.5 inch to the fourth, right? They're squares. So it's 4.5 inches to the fourth. Base and height are the same. Minus, we're taking away the hollow center, right? Minus 1/12, 3 inches to the fourth. So you wind up with 27.42 inches to the fourth. You plug these numbers in and you get a force, well, you get a force per unit length of 92.3 pounds per inch. Now, there's two things you got to do here. Well, one thing you got to do before you multiply by the spacing of the nails. We're trying to find it in the nails, but we need to recognize here that we've got two edges, right? This plank here is in contact with, it's got two seams. So this force is actually split between the two seams. So we just got to divide it by 2. So this is the edge force per unit length. Now you have that. Now you say, okay, what's the spacing between nails? You multiply that by the 1.75 inches, and you get a force, 80.8 pounds. Again, this is the force. So this would be the force acting on, say, one nail, right? And then based on what you know from earlier about shear force and designing things based on shear, you can select the right size nail of the material you need, right? What has the cross-sectional area. All right. We're going to look at, well, oh no, we're doing this one next. Shearing stress in thin-walled members. So now we've got this, this is an I-beam now. And what do we have going on here? Here we have an I-beam that has a, the bulk of the work really is being done by the central column, right? We've got these flanges off to the side. But if you take, let's just look at a segment, right? You cut down this B prime, well, B prime, or sorry, B prime, A prime direction, right? You're going to get a unit piece like this. So if we just look at the analysis of this piece, right, we get the same shear force, longitudinal shear force, again, longitudinal, right, along the length. This delta H, VQI, or VQ divided by I over delta X, right? We get that same equation for it. Now, if we want to find the shear stress for each of these positions, this is where the subscripts start getting a little fuzzy here. This is tau ZX and tau XZ. So let's look at what that means. Tau ZX means you're on the plane that's perpendicular to the Z axis and you're along the X direction shear, right? And then the other one is tau XZ, so you're on the X plane, which has got Z direction shear. So along the Z direction. And these are approximately the same, or those are the same, but they're approximately equal to this delta H, right? Oops. T over delta X, right, which is equal to the VQ over IT. You're taking the thickness times the delta X, that's the area, right, of that surface. That's your tau ZX, right, perpendicular to the Z direction along the X direction. what else do I want to say about that? If you recall from, oh, you know what? I don't know if I can find it. Hold on. Yes, if you recall from this element here, shear along a corner. Oh, whoa. Hold on. Oh, it's not here. Oh, what's this? No, it's not it either. Well, anyway, let's go back to this diagram because you can actually see it. If you shear it along this plane, right, you're going to develop an equal and opposite shear on the other plane, but also the adjacent plane, right? Shearing this way, well, the arrows are backwards on this, but if I take an object and I try to shear it this way, right, I'm also generating shear on the top plane there, right? The plane that's perpendicular to it. So that's what we're doing. And that's what they're using that identity for this tzx equals txxz, right? Because it's the perpendicular plane to it. So you generate the shear on one plane, you got to be generating the shear on the other plane next to it. And this is the expression for shearing in the web. Whoa. Tau xy, right? So now it's tau, the x plane, right? So perpendicular to the x-axis in the y direction is vq over it. And that's in the web. One thing they're pointing out here, is the xy, tau xy in the flanges is approximately 0, and tau xz in the web, so xz in the web, is approximately 0. So let's think about that physically, right? What's happening? You're loading up this beam, and the bulk of the load, the load itself is being supported ultimately by this, this center section, right? So any shear in the y direction is going to mainly be, that's why they say it's approximately equal to 0 in the flanges, right? It's mainly concentrated in the center section. That's the tau xy. So x plane, right? The plane perpendicular to the x-axis, y direction shear. And then in the web, right, the center section here, because it's handling all that shear, vertical shear, right? The sideways shear, the tau xz, right? So the x plane with z component of shear is approximately 0 in the web. But that's not the case up here in the segment. This segment up here, the tau xz is not approximately equal to 0. So you do have some corresponding shear due to the longitudinal stress. Oh, you know what? This is a stress element, but you can't really see it. Let me see if I can blow that up. Oh my God. I'm getting to the point here in the course where I broke the, last year I broke the course down into very short videos online. And you're probably thinking right now, oh, I wish I could watch those videos. So instead of lectures, or instead of synchronous lectures, I gave asynchronous videos. And so I was able to just do 3 or 4 slides at a time and keep it to I don't know, 5 to 10 minutes of lecture. And this blows up and shows you the tau zx, right, and the tau xz. So these are the ones up here, right? Those are the shears that we're looking at from the flange segment. Due to the vertical shear force. All right. Now that we know the vertical components and the horizontal components, right? We want to look at what's called, we're going to look at this shear flow, but before we introduce the term, let's look at the shear along different segments of this this box beam, right? So we got this box beam, and maybe it's extruded out of something, right? We're looking at a cross section, so it's lengthwise into the page, and it's got a certain thickness, little t. And notice the shear stresses. We got tau xz. So oh, let's see, x. Yeah, the x is pointed out. So on the plane here in the z direction, and these are dependent on this moment, right? Area moment. So we've got V, Q, and I. Now, I for the beam doesn't change, right? It stays the same. V, again, this is something we're putting on the beam. So really all that we're left with is Q, right? So as Q changes, it increases. It goes from this smaller, remember Q is area times Y bar, and Y bar being the distance from the centroid to the centroid of the object, the shaded area, to the neutral axis. And what's happening here? Q is increasing as it approaches, as you go outwards from, say, this position to this position, and then you keep going down, right? So the tau xy, right, these tau, the shear stress at the interface keeps growing. And you can see that denoted here with these arrows. Oops. Oh my God. PowerPoint used to be so good at stopping on the slide you were on. See these little arrows? The length of these arrows is indicative of the magnitude of the shearing stress. So what happens is it increases, 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 and then once you cross the neutral axis, right, it decreases, 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 decreases as the area, first area expands and then it contracts. So you get that sort of cyclical increase and decrease. Let's see. Oh, the sense of Q, right? The direction of Q is basically what portion of this are you in? So, depending on where you are in this beam, right? You can tell this is the XZ, this is the XY shear, right? Those shears change. The sense of them changes. All right, here's a wide flange beam. This is again showing the same concept as the box beam, except now we have this added line of symmetry down the center, right? So you really only have to look at one quarter of the beam because it's symmetric. It's symmetric about the y-axis. It's symmetric about the neutral axis. So the shearing stresses are going to increase, right, as you keep adding more area, keep adding more area, keep adding more area. It's going to reach a maximum at C, and then it's going to decrease again as it goes through to, here they call it point E. And this is based on, again, a vertical load, V, and the beam running in and out of the page. And you're generating a bending moment, and that's just this shearing stress as a result of that. They do here note that this continuity, right, the variation in Q, this stress per unit length, right, it suggests an analogy to fluid flow. Now, I've never really bought into that analogy, but it's more of a flow of shear concept. If you do more advanced shear analysis, you start to deal with that as sort of a flow in quotes. All right, let's look at, this is sample problem 6.3. We're going to just do this in the slides because it's fairly straightforward. So we got this, knowing that the vertical shear is 50 kips, right? So that's the vertical shear V in a W10 by 68 rolled steel beam. So if you're given this problem, right, you're going to go to your appendix and you're going to be able to look up things like the moment, right? Moment of inertia, 394 inches to the fourth about the centroidal x-axis, right? You can look up all the dimensions. It says determine the horizontal shearing stress on the top flange at the point A. So we're interested in that horizontal shearing stress. So we're going to look at the shaded area, right? This is our shaded area to calculate Q with, because we're looking at that that stress right there at that point, right, along that cut, if you will. In other words, if these were two pieces, right, which stress would you need to overcome to keep them connected? So you do your analysis again with Q. You've got the area. Well, yeah, 4.31 inches in width, 0.770 inches in height, and then 4.815 inches. This is the distance from the centroid of this shape, right, to the centroidal or the global centroidal x-axis. Shear stress at A. Let's see, what do we got? Oh, yeah, tau is just, excuse me, VQ over IT. Right, in this case, we're incorporating the thickness. So the thickness here, thickness of the flange, we got 50 kips times the 15.98 cubic inches, which we calculated up above. We got the moment of inertia, and then we got the thickness. Right, this is just right out of your shear stress equations. And the thickness is, remember that what's the face that's seeing the shear, right? That's this face. That's that thickness, 0.770 inches, right? So that we wind up with a shear of 2.63 pounds or 1,000 pounds per square inch, KSI. All right, let's do a little more complicated problem. Steel bar and aluminum bar are bonded together to form a composite beam. So this is kind of a neat application problem, because you may find yourself dealing with materials that are different yet bonded together, and maybe you need to somehow, well, you need to understand how is that strength of the bond, or what's required of the strength of the bond, right, for given conditions that it's operated under. So you know that the vertical shear in the beam is 4 kips. And the modulus of elasticity, they give you that for steel and for aluminum. 29 times 10 to the 6 for steel and 10.6 times 10 to the 6 for aluminum. Determine A, the average stress at the bonded surface, and B, the maximum shearing stress in the beam. And it's again, fairly simple beam, 3 inches tall by 1.5 inches wide. But it's 2 different materials, and we're interested in the shear stress along that bonded surface. All right, so the first thing we're going to do is we're going to normalize to one material. So first, normalize to one material. I'm going to choose aluminum. So I'm going to say, okay, I think it's just a little more, well, maybe it's probably a little easier to visualize. Aluminum has a stiffness of, where is it? Oh, steel, 10.6 times 10 to the 6th, right? And the steel is 29 times 10 to the 6th PSI. So the way we need to look at this is Ni equals EI over E reference, right? So for aluminum, this is just 1, right? The Young's modulus of aluminum over aluminum is 1. For steel, we've got 29 point, oh, just 29, well, 29.0 times 10 to the 6th PSI over 10.6 times 10 to the 6th PSI. This turns out to be, assuming I did my calculations correct last year, 2.7358 for steel. N is our factor that multiplies basically the area now, right? This is saying that if we treat everything in aluminum, or treat everything as aluminum, this is actually, as aluminum, right, it's 2.73, or sorry, steel is like having 2.73 times the amount of aluminum like this, width-wise. Let's look at this from the standpoint of trying to figure out our centroid. So remember, this is what we did when we figured out centroids. Our aluminum centroid's up here. Our steel centroid is down here. So I'll put centroid of aluminum, centroid of steel. Our combined is going to be somewhere in the middle. Again, we're figuring out the neutral axis for this thing. But we got to start off with, we've got two different materials, we got to normalize them. So the neutral axis, let's look at the part. I'm going to make a table here. We've got aluminum and we've got steel. The area is what I'm going to be multiplying by n, right? Because what I'm saying is the area, if this were aluminum, it would have to have 2.7358 times the area of steel. And let's do the math here. We've got, for aluminum, we've got 2 by 1.5, so we've got 3 inches squared. Oh, I've got the units up here. And then the other one we've got, or for steel, we've got 2.7358 times, what is it? 1.5. 4.1038. Yeah, I mean, it's just the area is 1.5, right? Times the n. So this is how much more area we need of aluminum than steel to get the same, basically the same stiffness, right? Or the same, well, same centroid location. Y bar I, this is in inches. This should all be fairly straightforward. I'm going to choose my Y. Let's see, where did I choose my Y? Hold on a second. 2 inches, 0.5. Yeah, I chose the Y down here. So for aluminum, my Y bar is 2. For steel, my Y bar is 0.5. That's for the centroid. Now we've got NI or NAI Y bar I. And that is going to be 2 times 3 is 6. 4.1038 times 0.5 is 2.0519. From here, we can find the centroid, right? We sum these up. Here we've got 7.1038. Here we've got 8.0519. The global centroid is just equal to, again, the generic equation, which you should remember. I don't even remember the chapter. You guys have better memory than me because you're younger. I was just lamenting with a friend about brain fog the other day. Just sum of the AIYIs, in this case times n, divided by the sum of the areas for composite beams, right? 8.0519 divided by 7.1038. And this gives you 1.1335. This is your neutral axis. That's the location of your neutral axis. So let's look at where approximately where that falls. 1.13. So I'm going to put a little, exaggerate it a little bit. In fact, this is what? This is 0.1335. This distance here, this height. I should have put the arrows on the top. That. Right, because this is already 1 inch. So this is our total centroid right here. I'll write it in red. Now we want to figure out the moment of inertia for this thing. We got to find our D value. If we remember that, D is the difference between, it's basically Y bar minus little y bar. So the global centroid minus the local centroid absolute value of. So what do we got? We've got, this is at 2 inches, basically minus the 1 point, let me do the 2, minus the 1.1335. Yeah, so 0.8665. That's the distance from here to here. Now we're looking at the centroid for steel. Distance from here to here, that's going to be the 0.5 plus the 0.1, right? The 0.1335. So we're going to get 0.6335. To get our moment, right? We're going to take, or the correction of the moment, I guess. We're going to take the, let's see, what did I do here for? I better do the math down here. NA P squared. Well, this one's fairly straightforward. We're just multiplying here the NAI, right? The area times the N times D squared. So this value here. So we're going to get 2.2525. And then here we're going to get 1.6469. The sum of all this is 3.8994. Let me do N I bar, or yeah. So this is the moment of inertia of each one of these individual components. So let's do that down here. N I bar aluminum is 1/12 base times height cubed times, well, that's an N. I just took the N and put it, I should have put it over the 12. So we've got 1/12. For the aluminum, our base is 1. Our height, oh, sorry, our base is 1.5. Our height is 2, and that's cubed. And our N is 1. So you wind up here with 1 inch to the 4th. Basically, so 8 times 1.5 gives you 12. 1 inch to the 4th. So that's what this is. For the steel, I'll put the N over here. We still have N over 12, base times height cubed. And here we wind up with N in this case is 2.7358 divided by 12 times 1.5 times 1 cubed. And this gives us 0.3420. I don't know, you can add these together and have another column, but I didn't have room. So I'm just adding these up over here. 1.3420. The overall I is going to be the sum of these two things, right? The sum of the N A D squared plus sum of the N I bar. What do we got? We've got 5.2414 inches to the 4th. All right, this is just setting up the problem. Now we can actually find the average stress. Right now we've got our moment of inertia for the composite beam, right? Because it's two different materials. You can't just take geometric moment of inertia here. You've got to solve for it, based on the ratios of the Young's moduli that are given. All right, so tau, what am I going to call this? I'll call it the bonded surface, BS. Tau BS. It can be V, Q, over IT. let's see. Where did I get my, I feel like I skipped a step here. No, I didn't. Oh, yeah, I just skipped the multiplication. Hold on, let me do it on the calculator, make sure it's correct. What do we got? 3 times, what's the y bar distance? Oh, there it is. 0.8665. Yeah, okay. Q is, I'm going to expand this out. So I've got V. You know what? Let me just scratch this out. Q is going to be the NAI times the y bar. And we're looking at the top section here. I mean, you can do it about the bottom section too. In fact, you know what? It should work out the same number, 4.1038 times, what's the distance here? 0.6335. Yeah, the same number. So let's take, we're looking at the neutral axis is right here, right? So we're looking at this seam. We want to know what the shear stress is in there, right? And this is the area that for Q, but we're using the NAI y bar, right? Because this is steel. It's a little different area. So that's going to be 4.1038. Let's put a note in here for steel. And then y bar we already have. This is, again, remember, that's the difference, distance from centroid to centroid, sorry, part centroid to overall centroid. And that's going to be actually this distance right here, 0.6335. And we should get 2.599, well, depends on how you round it, 995 or 997, 2.55. Oh, not 55, 59. 9. Did I do that number right? 4.1038 times 0.6335. Yeah, it looks like the other time I did it the other way. So we'll use an 8 here. 2.5998. We know Q now, we know I, we know T, and we have V. Let's watch our units here. 4,000 pounds. Oh, we don't have units for Q. What is this? This is going to be area times length. So this is going to be inches cubed. 2.599 inches cubed over what? 5.2414 inches to the fourth. And the thickness here is just the thickness, it's the width now, right? You're looking at you want to find the shear, right? The stress at the bonded surface. So that's the stress on that surface, right? And the area is basically, it's in and out of the page, but it's the width that you're using. Width of that surface. That's what the thickness is. 1.5 inches. Now I'm curious about my rounding. 4,000 times 2.5998 divided by 5.2414 times 1.5 gives me pretty close. 13, yeah. So I'm going to just round it here. 1323 psi. That's the stress in the bonded surface, or at the bonded surface, part A. So this is the stress that bond, right, is going to experience. 1,323 pounds per square inch. And obviously the square inch comes from the fact that there's an area here, right, in and out of the page. And then B, part B, We want to know the maximum shearing stress in the beam. So tau max occurs where Q is at its max area above or below the centroidal neutral, above or below the centroid or neutral axis. Right? This is what we learned with those shear flow diagrams. The shear increases up to the neutral axis, then it starts decreasing again. So Q max is a y bar basically divided by 2. Well, I mean the whole A. So let's just take one of the numbers here. 1.5 times 1.8. What did I choose here? It looks like I chose the 1. Oh, I chose this area here. So it doesn't matter, right? This is the neutral axis. It doesn't matter now if you go from above or below, right? The max is going to occur here. So I'm just taking the top portion, the one that's where the 1.8665 inches comes from. Right? And then there's the distance, the y bar is 1.8665 divided by 2. Right? That's that distance. This is this distance here, right? This distance is 1.8665. Right? The distance between the centroids is just divided by 2. Because it's the centroid of the area above the neutral axis, not the centroid of the aluminum. It's the centroid above the area, or of the area. So here we have 2.613 inches to the third. So tau max is just V Q max over IT. So all we're doing is we're doing the same equation as before, except we're substituting a new Q in. We got 4,000 pounds. We've got the 2.613 inches cubed. 5.2414. And then 1.5 inches. So this turns out to be 1329 psi. So tau max is 1329 psi. Ooh, just enough time here. This is basically how you do the problem. Let's see. One comment about the steel. I just want to sketch it out up here. When we do this, I'm going to run out of room. I'm just going to put this in a little bubble. If we have aluminum steel like this, what we're doing with this N is we're basically making it look, we're making a beam that looks like this. Functionally, it's equivalent to something like this. That's all aluminum. So aluminum, steel equals aluminum. Let's put a little cloud around that. I didn't really have another place to put that, but this is what we're doing this is what you're doing when you're bonding two materials like this of different moduli, right? The one that has the higher moduli or modulus is acting like a wider, right, like a wider plate, right, of the same material. So that's what we're doing when we're normalizing this with respect to the Young's moduli. This was in a previous chapter, but I just thought I'd refresh your memory up there. So that's how this works. All right, I have nothing more to start, I think. Yeah, we'll do this next one on Monday, and that should wrap up the chapter. Are there any questions about anything? All right, if not, have a good weekend.